Okay, what is the first test?
The first will be the instantaneous,
Okay.
or we just put the definite time and they will we will send the settings of the pickup current, then the time delay, and we will see it. And then the
Instantaneous. We send the signal and the guide thread. Yeah. What will be the time that? Because you said 0.02 or
we can use 0.3.
okay 0.3.
Yeah.
Okay, 0.3.
And this
But
is
that
the
is the
definite time.
definite time. Yeah. Okay, the first test will be definite time. But do you realize that the breaker is still closed?
Yeah, because I am not sending any signals.
Ah, okay.
No, but it is not closed. You remember that it is breaker closed? Okay.
Yeah.
But I am using.
No, but this is breaker close.
Yeah, because I am using the accelerator and I need to.
Okay. First step, definite time, 0.3 seconds. We will see the signals, yes? And the SCADA, we will see the signals, okay? And it's a good idea that we make comments about this, okay? That you can see how the voltage going to zero. No, this is the current, yeah.
How
The-
the voltage.
The voltage
decrease
decrease during the fall, yeah.
and after the breaker opens, the
Current goes to zero.
goes to zero.
Very good. Then,
Inverse definite. How is the name of it? What is the name of the other one?
inverse time.
Time, and we will pick a curve,
Curve.
dial,
Dial.
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 And we will insert a form and let me see because this is not working. Okay, this is will not change
Image.
the place. Yeah, because I can't find what is the problem.
The path of the image.
Yeah, but I am
Oh, let me close the. key. Are you ready, Marta? Or it's not working?
Just give me a second. I will remove this because, or should I keep it?
If the value is crazy, remove it.
Yeah. Okay. Because it is bigger than the operation, but we can say that it is the clearing time since the fall starts until the relay operates.
Okay. What I will do is I will go to find the students, okay?
Okay.
And from there, what I will do is I will come back here, and there is a presentation that I will take probably 15-20 minutes. Then I will go through all the equipments, yeah? And from there I will go to explain a bit about what they are planning to do, and then it will be your job, okay?
But okay, me alone?
Of course, I can help you, but you are the star. You will tell, okay, right now we are doing this, we are doing that.
Okay.
Explain. I don't know what you are planning to do. That is the reason that. Okay, I will come back, okay? You go and find the students. First step, get the students. No, no, all of you, where is your mask? Where is your mask? Oh. Okay, please move here, yeah.
No.
You don't want to have a chair? Oh, it will be,
Long?
it will not be long, but if you want to sit down, it's okay, because I will sit down here. What is the idea? Okay, I have a small presentation. Take the chair, it's much better. Marta, could you put the presentation here? No worries, they are only for students, okay? And holy internet, okay? No worries.
Oh, but it should be inside the machine.
I'm sorry. No, it's okay, it's okay. You can sit down. It's not presenting over there because you need to open the other machine, yeah? Okay.
I will do that.
Don't fall in love with them because they are not the most friendly things that you will find in your life, okay? A lot of people right now, they are talking about digital media and digital stuff, and they don't have any idea what is that, okay? I am a power system engineer for many years, and I am surprised how difficult the things are here, okay? Okay, let me start with a short explanation about, let me take that machine.
Sorry. I can move my chair.
Yes, I am using this one, okay? Let me start this presentation with something simple, okay? What was the idea behind this lab, okay? I took a decision in 2019 of coming here to Norway, and every time that you move between countries, you need to start again. And that is really, really hard, okay? I was 15 years in South America. I created my research group over there. Then I moved to the UK. I was in Manchester, the University of Manchester. Then I was in Coventry. Then I was in Loughborough. And then I moved here, okay? And every time that you move, you need to create from scratch. You need to start to create things from scratch. And when I arrived here in Norway, I have a very bad news, okay? Because for many years, I was teaching power systems, and suddenly somebody asked me to teach protections. And for me, protection is a very serious topic, okay? Not much people put their hand on relays, and a lot of people, they use just the paper and just solve the problems on paper, and that's all, okay? To be honest, last year we did in that way. Last year, when those students took protections, they just set the relays on the paper, and that's all. And to be honest, that is a Mickey Mouse problem, okay? Why is a Mickey Mouse? Because in reality, going into a real relay is more complicated, okay? In 2020, I decided, okay, if I need to keep teaching protection, I need to do something else. And what was the plan? Well, create practical experience that people can have the real relays, go inside, see what is inside, settings, prepare everything, okay? However, relays, they are extremely complex, okay? The things that we see in class is just tiny, it's almost nothing, okay? However, don't be overambitious, because this lab also we will do small stuff, but it's the next step, okay? Okay, I decided to create the lab. Then I realized that in Norway, if you want to have a lab, you need to apply for infrastructure, and it's with several universities, several millions, and so on. And then I was, you cannot do that. And then I start to talk with several friends in different companies, Cell, ABB, Typhoon Hill. I say, I want to do this. And then they realize, okay, let me support you, let me go with your initiative, and we start to get equipment, we start to get information, we start to get many things, okay? And that was the starting point of this, okay, the lab. What is the motivation? Power systems are changing, but they are changing not just in the generation side, okay? When I was teaching about power system, I told you that the power systems, we are including more renewables, we are including more converters and so on, but that is one side of the history, okay? Changing generation means is just a very small size of the whole picture. One important component of this is that we are installing components everywhere. They are converters everywhere, but those converters, they can take advantages of information communication technologies, ICT. And that is where everything starts to change. Many years ago, we called these relays. Today, we call this is IED, Intelligent Electronic Device. Because right now, they are doing more, far more than just a basic protection function. Inside those devices, we have many kind of functionalities, starting for sensors. We can record here events, we can record power quality, we can record almost everything, okay? Then we have control actions. We can define any kind of controller. If we know the proper language that those devices has inside, we can program any kind of controller, okay? And finally, of course, they have the protections, okay? But that is just a small part. Those devices are doing far, far more compared with many years ago, okay? Oh, Jesus, this is in a wrong place. The relays is in a wrong place, okay? We are moving from there, very old relays. Those relays we call electromechanical relays, okay? In the UK, I still having some of those very old relays. They are amazing. But now we are using those devices, okay? And those devices, they are completely different. Those devices, they are in the digital era. They are, to be honest, in a minute we will discuss about what is inside a relay. But inside a relay, they are more power, more computational power than in a basic computer that you can find anywhere, okay? Because we have not only computational power, we have digital converters, we have some kind of devices that they are very specified, specialized hardware, and those devices are extremely powerful, okay? But we are changing, okay? We are changing. I will not keep moving this, yeah?
There is a mouse over there.
Where is the mouse? Oh, you have a...
Another one if you want to.
Oh, no, it's okay. I can do it from here. Okay, over there what you can see is that the original history about protection was this, okay? A relay. Our current relay, that was probably the origin in 1920s, 1919, something like that. But now we have metering, for reporting, for recording, for location, monitoring. I mean, these devices start to do many things more than the classical protection, opening the circuit breaker. They are doing far more, okay? And why they are doing that, okay? Because at the very beginning, we create the electrical power system. We have the electrical power system, the classical infrastructure, we have generator, transformer, and so on. And in parallel, this was growing and growing, okay? For many years, we start to install telephones, then we start to use mobiles, the internet arrived, and that was the starting point that internet allowed communication between the physical system, that is the power system, the generators, the circuit breakers, everything, and the cybernetic component that is basically communication, informatics, computer, and so on, okay? And that was the starting point of the concept of a smart grid. That was the moment that people start to talk about smart grid, the integration of the electrical power system, many areas inside the electrical power system, and also the communication system. However, at that moment, people start to talk about smart grid, but it was just basically adding functionality from internet and computational power, but it was not totally merged. I mean, still a layer for communication and still a layer for power system devices, okay? That was cyber physical devices, okay? The situation started to be interesting a few years later, okay? Because we start to make the communications between the different IDs and some control centers, okay? We have been using SCADA for many, many years. SCADA is one system for monitoring, data acquisition, and so on. But then we start to use those SCADA together with some other functionalities. For instance, demand side management. I mean, right now we have a lot of converters downstairs. We have electric vehicles, and those converters, they have the possibility that you can plug over there and you can send signals and do whatever you want. Okay, if the user allowed to do that and you pay for that. Okay, don't take me so general. But this communication link start to create the fusion between the communication channel and the physical layer of all those devices. And that is the moment that we start to have communication systems, but very specialized for electrical power systems. For instance, IC 61850, that is a communication framework. To be honest, it's a framework. It's not only communication, it's not only information, it's a framework for making the electronic components more intelligent and fused with the electrical devices. That is the moment that we start to merge together cyber components and physical components, okay? IC 61850 is probably one of the most important framework for communication, information, and processing, but there are many others, okay? Inside the electrical power system, there are many. For instance, this ZigBee has been used for monitoring and controlling things inside houses. Wi-Fi can be used as protocol to send signals going, and that was, for instance, used for smart meters, okay? But there are many other kind of protocols, okay? In this course, we are not talking so much about 61850, but all those devices, they have that capability. All of these, all of them, they have the capability of talking using that communication protocol. In fact, one of my master students, he is working with 61850, creating signal from the real-time simulator and sending signal to the relay, okay? Because right now, you don't need to send 5 amps or 10 amps in order to take the measurement here. Right now, we have the possibility of sending zeros and one, I mean digital numbers, that they can be read by this device and transformed into information, okay? Okay, good. That is good. Okay, what the hell is this? You are here because this is the DGNC's lab. I don't know how to say that. I create this name, Digital Energy System Lab, okay? Why I call this Digital Energy System Lab? Because we are including physical components, but those physical components are interacting, to be honest, using digital simulation, digital devices, okay? That is the reason. And also because I am totally sure that power system will end in one moment, okay? I have been teaching power system for many years, but electricity must be merged with other kind of energy system. Hydrogen is coming, transportation is coming, heating and cooling is coming, and as consequence, all of this will merge, and that is the reason for energy. We are not just talking about electricity, we are not talking about just power, we are talking about everything. And there are 3 main areas that we are doing here inside the lab, okay? There is what I call the cyber physical system, okay? Cyber physical because we have those things They are physical, totally physical, but we have the capability of using relative expensive equipment to create signals that they are coming from real-time simulations. Okay, in a minute I will tell you the challenges about real-time simulation, but here we have those relays. We have the cell 751 feed and protection relay. We have the cell 411L. This is a differential line protection. Here we have the ABB 640. This is a monster. This guy is almost doing any kind of protection functionality. But also we have the other one. I love this one. This was my first relay. This is ABB Ref 630. This is a feeder protection relay. Okay, this is the very, very old version of that one, the Cell 751. Okay, it's doing almost the same functionalities, but this is a bit older. Okay, okay, but then something that you cannot see here is at the back of those two racks. We call these racks. Okay, at the back of those racks we have the communication infrastructure. Okay, because for sending signal from here to there, or to that computer, or this computer, or this computer, or to internet, or somewhere else, I need to use communication channels. Okay, and in this case we are using the classical TCP/IP protocol for communications. That is the protocol that you use for internet. What you need is just a single IP. Okay, here we have several switches. We have two switches, we have firewalls, we have also routers, and that means that we are able to replicate the real behavior of two different substations. Okay, I don't know if you can see, but here this is station A, station B, station E. Each one of them has a number, because if we want to do 4 or 5 different substations, I can do it, and I can communicate those substations using the communication protocol. Okay, that is a very interesting thing. Not much people do that, because you must understand the communication protocols. That is the reason that I took this year one master student to do a project, and it's basically generating the signals and sending back to one ID for processing. Okay, and then we have some other features here. We are doing also something about artificial intelligence, and we have here this big computer, and that computer is around 60 teraflop of trillion of mathematical operation for floating point operation per second, and that is basically for artificial intelligence. Okay, I have few colleagues around the world that they are collaborating with me. They are using the remote access, similar to the things that you are doing. You will access the lab using that computer over there, and that is remote access. Okay, you will go into that computer, and when you go inside this computer, you have access to one of the local area network here. Okay, okay, let me keep going here. I believe I told you that we are moving from offline simulation. The Excellent Power Factory is running offline simulation. Okay, offline simulation is you press the button, you don't care about the time. 3 years later, you get the results. Okay, that is offline simulation. I am being a bit, let's say, saying 3 years. Okay, but time is not the important thing over there. Okay, when you are doing Power Factory, you don't care about the time that you need for calculating all the results, because it's not critical, because you are not closing the loop, because you are not acting with a real component. Okay, however, Power Factory realized, and many software realized, that the systems are changing so much. Hydrogen is another energy sector. We have transportation, we have another kind of things, and all of them have different kind of models. Okay, and those models, they are very difficult to create. And that is the reason that Power Factory is doing pretty well in electricity, but they are able to connect with another softwares. Okay, for instance, you can use Modelica, you can use any kind of application, you can use any kind of other software for modeling and simulation, and you can make the connection. Okay, what you need to use is one of those communication protocols. You can use OPC, you can use C++, you can use Python, you can use an IP. API, and you can connect with them. Okay, however, this is let's say this is the second stage when you are doing simulations. Okay, first step is offline simulation. Second step, co-simulation. What is the next step? The next step is real-time simulation, okay? And real-time simulation, you need a workstation. In this case, this is the workstation. Here you have a software. Inside that software, you can create your models, okay? For instance, in this lab, we will have the model of the network here. And then we can compile that model and send that model into the real-time simulator, okay? And what is the real-time simulator? In few words, is an expensive computer. And inside there are two main components, okay? We have the classical CPU that you have in any kind of computer. A CPU is the classical processing unit. You can have a Intel or you can have a ARM. You can have different architectural topologies or whatever. But then you have this, of FPGA. FPGA is a hardware that is able to be reconfigured by software. And when you reconfigure the software for your model and you put the model inside, this is able to run extremely fast. Okay? To be honest, FPGA is able to run faster than 4 GPU, is able to run faster than 1 CPU, because it's optimized for the very specific model that you are doing. Okay? For instance, here we have, this is the Hill, this is the Typhoon Hill, this is the 604. Inside this guy, there are two different, there is a CPU and there is a FPGA. And here I have another real-time simulator. This is the Opal RT, the 4210. This is a very old version, but it's still working. Inside we have a FPGA. If I remember, that FPGA is a this ceiling. No, I don't remember the model. Okay, let's keep going here. And then, what is the challenge? What is the challenge? Why we call this real-time simulation? We call here real-time simulation because here we are using time that is totally real. Because, for instance, if you need to send a signal to one of those devices, voltage, currents, those voltage and currents must have the specific shape, the specific sampling. Everything must be real signals that we are sending. And those signals, if we have a model inside this, that means that we need to solve the model in a very small time. And that is the reason of this. In real time, what we are doing is solving step by step the model. In a computer, offline simulation, Dixieland Power Factory, you are solving the model step by step. But when you are doing offline simulation, you don't care how much you spend moving between one step and the other step. You can spend 3 seconds, 5 seconds, you don't care, because you don't have any problem sending the signal somewhere else that they must arrive on time. What I'm telling you is that for each one of those points, they are creating a signal that must go somewhere else and then going into the relay. And that must be done in a very small time step. And for instance, a classical real-time simulation, we are talking about time step of microseconds. That means that you have around microseconds to do many things. For instance, receive the data, process the data, and then send the data. Okay? This is for the CPU. And then you have here in the FPGA, because there are some processes that they are faster than others. For instance, if you are doing power electronics, you need to use the FPGA, because the time scale is very small. We are talking about nanoseconds. And if we are taking measurements, if we are collecting data, we are using the CPU. And that is microseconds, okay? Now you can see the challenge. The challenge is getting a solution of one model in time scales of nanoseconds, okay? Okay, but that is mathematics, that is another job. Why you are here? Because we are doing this. That is what I call relay in the loop. relay in the loop. We have the model. We put the model inside the simulator, and then we send signals to the relay. And if the relay open, well, it will send the signal back and say, I open, okay? That is one way to test the relay. That is the best way to test the relay. Okay, I believe you saw this. There are two different approaches for hardware in the loop. You can use the real-time simulator, take the signals, and go into the hardware directly, okay? We can do that here. We can take signals, low voltage signals, apply to a low power device. That is the concept of control in the loop. But if we need to send real signals, for instance, this guy is receiving 183 volts. That is and 5 amp, up to 5 amps. That means that you need something strong and expensive to create those signals, okay? And that is power hardware in the loop. Power hardware in the loop is what you are doing, because we are creating the signals inside here. We are going out with very low power. Then we go to the power amplifier, and from the power amplifier, we are going into the relay, okay? And this is the history that I am telling you. We will have here a small power system. In this system, we will put a fault, and you will see the current. And that current will be generated here and sending here. And if you want to install the oscilloscope over there, you will see the real signal, okay? But also this device is able to record the signal, okay? You are able to see the real short circuit current, and if this guy trip because the setting is right, you will see how the current is stopped, okay? That is beautiful, okay? Okay, now it's time for Marta.
Hello.
She is the mother of the lab, okay? I am the father. No, we are not married, nothing like that. She is my PhD student. She is probably my daughter, and she has been extremely working with this, okay? We have been working here for probably more than 1 year. All those cables over there, in a minute I will show you cables we did by hands, by ourselves. She's my PhD student over there. He arrived quite recently, but also he has been working hard here. And well, she is the brain behind the final real-time simulation, okay? All yours.
Okay, good afternoon. Welcome to the laboratory. I will try to show you how the cell 751 communicates with the Hill 604 and using the Hill Connect. I will send some signals from Hill 604 to the cell, and it will detect if there is a fault or not, and we will receive feedback to the model to see if it trips or not. It sounds a little easy, but it is not so much because it involves some Python code to communicate with the relay using the word bits. You must be familiar with the word bits of the relay, because every relay has a different word bits. It depends of the model. It doesn't matter if it is the same brand. You need to be familiar with.
Let me explain the phrase word bit. Word bit is a very specific language that the relay uses inside to decide the functionality and if the relay moves up. That is a word bit. And inside the same brand, for instance, those blue one over there, they are cell. But inside the same brand, the word bits change. I mean, you must be familiar with the words of this guy and then with the words of that guy in order to send the proper words to the relay in order to work, okay? Keep going, my dear Martin.
Well, I will start to show a little or give a little explanation about how the Hill SCADA works. and then I will try to run one example to see what is the signal that the cell is receiving, and what happens if we have a short circuit, if the breaker opens or not, and how we can receive the signals here.
Okay, good. You can start to prepare everything, and I will make an explanation. Okay. In classes, you learn how to set up the pickup current, for instance. If you are using overcurrent functionality, the pickup current is the current from where you are in a fault. And if the relay receives a current that is above the pickup, the relay must send a signal to the circuit breaker and open the circuit breaker. That is basically the idea, okay? However, how are we doing that, okay? Over there, oh, what did you do? You close off it.
No, it's open, sorry.
Okay, over there we have,
I'm sorry.
over there we have a small power system, okay? We have here a source, we have here a step-down transformer, we are going here, there are two loads, there's small transmission line, and here there is another two loads. And in the middle, we have installed, virtually, we have installed this gentleman over here, okay? What is doing this guy? This guy is sensing signals going into the relay, and if the relay see that the current is above the pickup, he will send a signal back. And they will tell to the circuit breaker to open and disconnect everything below, okay? For that reason, if we have a fault here or here, this relay should see the short circuit current and automatically will go above the setting, and this guy must open, okay? Two things that we need to realize, okay? When there is a short circuit, you will see that the current is going up, of course, the voltage going down, yeah? And after this relay notice that current, and this is a real device, it will take time. After that, the relay will open. Sorry, the relay will send the signal to the circuit breaker, and the circuit breaker will open, okay? That is the idea. But before that, I keep open this one just to show you. If you want to come here, that is the reason. No, you can go over there. Don't put your hand inside, but just want to show you all the cables inside, okay? No, you are not seeing. You can see here. Okay? And also, there are cables here. This is the small, you can see here, this is the cables coming from this guy. In blue color, we have those, okay? That is only for this relay. This is the Ethernet cable going to the switch, going to the communication, going to the computer, okay? And here we have another relay, and you can see all the cables, okay? Just creating the cable was a nightmare, because you need to identify where it's connected, what is doing where and how, okay? Okay, are you ready, Marta? This is the schematic. If you remember, I say to you, please be familiar with the Hill SCADA. Here we have the schematic, we have the network, we have all the data about the network, resistance, reactance, voltages, blah, 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 okay? Now Marta is preparing to send the signal, isn't it?
Yeah.
Are you ready?
Yeah. First, you will working with this software, so I would like to explain you that it is a simple way to load a model. It just you need to click on this icon, open model, and you will search inside the proper folder, and you will just select the...
I will give you a document where I tell you this is the file that you need to load, and you will find the file and you will load the file into the schematic, and everything should be done, okay?
Yep.
Okay, good.
Once you select the model, click on open, and it will open the model, right? And in this case, you need to take care about the the output window, because if something is wrong with the model, the output window will show you a warning, and it will stop the compilation of the model. So you need to take care about this output window, and if everything is fine, you will see the compilation finished successfully.
Here.
Okay? I will. The next step is just compiling and load the model from the schematic editor to the SCADA, to the Hill SCADA, which is the software that allows you to communicate directly with the hardware.
That is the short explanation. When you press that button, what you are doing is compiling the model. You are transforming the model from the code that is generated by this schematic, and then is compiled into C and sent to this guy over here, okay? And when you press the button, okay, press the button.
I will clear this.
Okay, now you are compiling, and you can see all the activities that they are happening. First, there is a safety check about memory, about location of resources, and so on, because that is quite critical, okay? If the model is not able to be solved by the hardware, they will stop and they will give you an error, okay? But if everything is fine, and Marta did, everything will compile, and at the very end you will get that green lights that say you are ready, okay? Now the next step is she will open what we call the SCADA. The SCADA system is the software that is allowing you to control the simulation, run the simulation and control the simulation, sending signal and receiving signals, okay? Now let's go, Marta.
Okay, when the model is compiled successfully, it will open automatically the Hill SCADA interface. In this part, you need to be careful about this, because in this case we are working with a real-time mode. That means that we are connected to the Hill 604.
Okay, let me make the explanation here. If you download the virtual Hill, and I ask you to download the virtual Hill is just running inside your computer using your CPU. When you are using the virtual Hill, you have many features that you can use. However, you cannot do real time. Why not? You are doing real time, but you cannot send signals and receive signals, because you don't have the real device with the cables able to go into a real thing. For that reason, in this exercise, that is the reason that you need to use that computer, because that computer is connected to this device, and now you can run a real-time simulation, a real one, okay? Now, Marta, run the thing.
Now I will load
The
the
SCADA.
Hill SCADA model,
Yeah.
and this is the one. Now this is the model.
Yes, as you can see over here, the original system, okay, the original system was the external grid that was a voltage source. Then we have the transformer. Then we have the circuit breaker together with the relay. And then we keep going down, okay? This is a very simple system, but what we want to do is include a short circuit. And if there is a short circuit, this relay must identify the situation, send the signal to the circuit breaker, and open, okay? I think the first simulation that Marta will do is just send the signals without any fault to the relay.
Yeah.
And you will stop over there because I will show them that there is real current coming here, okay?
Okay, once you have the model here,
Yes.
you just need to press this button. You can see this button? On
The one here at the top. When you press over here, you can see that right now it's in red, and you can see the real time, okay? This is the time that you have in your watch or your clock, and this is the real time that is happening there, okay?
Just here, these signals, alarm, closed circuit, and trip circuit, those signals are measured directly from the cell 751.
What she is telling you is that these are real signals, that they are measures at the back of the relay. When the relay is on, you can see here some LEDs, okay? But those LEDs are for local information. You can send that information somewhere else if you are able to identify the cables and the connections and so on. And we are taking that information and sending back to the real-time simulator, okay? That is the reason that you will see later when we have, for instance, when we open the circuit breaker, you will see that the circuit breaker will change the status, and you will see here also changing on those LEDs, okay? Keep going, Marta.
I will send the signals in order
Yes,
to
please.
you see the.
Hopefully, finger crossed, today will work properly. Last night was not working.
Now I am sending signals.
Okay, let's see if you are sending signals, okay? Okay, let me tell you the following. Students love this cell 751 because they have the touch screen. The touch screen is lovely. You can come here. This is like iPad. And you can do everything with your finger like you are doing with your mobile, okay? Students love that. This is a relay, probably 2018 or 2019. That is the reason that you have the touch screen. This is also, I think this is 2019 or 2020. Also you have the touch screen. But if you are in a substation, you need to work with these 4 keys. Sorry. The thing that you are looking here, okay, is fine, but if you want to see the currents, you need to move, Jesus, escape. Okay, no currents, here. You can see here the currents, it's pretty nice, you can see in colors, but if you need to do anything else here, you need to use those push buttons, okay? And here is the same history. If you want to do anything else, you need to do by hand, okay? Is good the touch screen? I don't know, students like it. I really sad because I didn't have the time, I must be honest, because I didn't have time to make the configuration of this relay because we were focused on that one, okay? But this relay, ABB is quite clever. They create a app. And if you want to see the settings or send the settings or do anything with the relay, you can do with the app. I mean, now the things are making easier the job for the power system engineers, okay? However, of course, these kind of applications, they have a lot of cybersecurity, password, considerations about security, okay, cybersecurity. Because right now we are using a lot of technology, digital technologies, but also open the door for bad people to do what they don't need to do, okay? But now the important parts, Marta is sending signals over there. Don't do anything else. Could you see this?
Yes.
How many?
1.2.
Huh?
Yeah. 121.
That is 100,
121.
121 amps, yeah?
Yeah.
Yeah. Okay, let me go back here. This is the bay, this is the meter, this is the phaser of the voltage.
Oh, no, 11 kV.
No, this 11, 1100 something. Okay, could you see here that you can see the voltages, you can see the currents, you can see the angles,
Yes.
and this is perfectly a three-phase system, okay? Probably you are saying, come on, this guy is generating 11 kV? No, no. This guy is generating the voltage from the secondary of the voltage transformer. Remember that we have the CT and the VT. The VT is the voltage transformer. We can have 11 at the high voltage side, and we can have 200 or 132 or anything low voltage of the voltage transformer, okay? But here, the current is 122. What is the transformer ratio? Do you remember the transformer ratio?
It should be 200.
200. We divide that by 200, should be around,
No.
it's 200, are you sure?
Yeah, it's 200,
But this is the nominal current. This
Yeah.
is the nominal current. Should be below 1 per unit. Yeah, one amps. Yeah, let me see. Where is my calculator? Calculator here. 122 divided by 200. We are sending from here 0.6 amp. Okay, 0.6 amps is able to kill somebody. Okay, and also I didn't tell you, but here we have 48 volts DC, enough to kill people, and we have also 25 volts DC. Okay, and when we use the big device over there, we can reach 125. Okay, but we will discuss about that device later. Okay. Well, there are more information that we can see here. For instance, we can see RMS values. Okay. We can see here also energy if we are supplying a load, and we can activate this, and you can get more information, including harmonics, including the device is doing many things. Okay, it's not just protection; it's more than protection. Okay, and one important thing I didn't told you. Okay, this is a relay. This is a relay. This is a relay. But I didn't tell you about this beautiful guy here. Do you know what is this? You can read over here. Synchronized satellite synchronized network clock. To be honest, this is a very expensive, because this device is a clock, but this is a clock with a resolution of nanoseconds. That means that it's using an antenna, receiving signal from satellites, and calculating the time. This is the real time right now, okay? And the interesting thing is that we can get this time signal, and we can put inside the relays. And that means that we can synchronize all the measurements at the same time. For you, probably it's not relevant, because for many years, just overcurrent has been a local protection. We need to open the circuit breaker when there is so much current. But there are many other protection schemes that they receive the name wide area protection and control. Wide area protection and control means taking measurement in several places. And if you need to take a decision based in several places, you must be sure that everything is happening at the same time. And that is where this clock is coming, okay? And the second device here is also a clock, but this is a PMU. This is probably the second or third generation of PMU. This is a phasor measurement unit. This device is capturing measurements, phasors like this, of these voltages and currents, okay? Well, let me come back here. What is your plan, Marta?
Okay. Right now, the Hill SCADA allow you to communicate directly with the relay. Instead of go to the relay directly, you can send parameters over here using a Python code to communicate with the relay.
Okay, what she's trying to tell you is that in this exercise, we can modify the settings of the relay. And there are different ways to modify the settings. One way to modify the settings is coming here to settings, and you can go inside global, for instance, and you can see, for instance, here the frequency, nominal frequency. You can see the sequence, connection, and so on. Okay. Every time that you try to change something, he will ask you for the password. Okay. Okay. Let me go back. But also, let me go down. No, there is no more here. Let me go to the group. No, to the group. And inside the group, you can see line 5. No. You are doing right now overcurrent. Yes, instantaneous overcurrent.
Definite time of overcurrent.
Okay.
Like
There is a reason that I don't like the touch screen. Because if you move your finger, or you have those fingers so big like mine, no. Here you can see all the functionalities that this relay have, okay? For instance, you can see that we have frequency settings, vector shift, power factor. You can see over here, over voltage settings, inverse time, all the settings, but I don't find directional, neutral over current, yes, line,
It is the maximum phase over current.
this one, yes. Here you can get the setting for the protection 50, that is the ANSI number. The ANSI number 50, you can set up the current from where the current from where you will start to see a fault and the relay will open. Okay, you can change this here if you have the password. Okay, that is one way. That is local. Local, you can go to the relay, press the buttons, change the settings, and so on. There is another way. There is an Ethernet cable. It's inside the network. There is IP address. You can use a software from Cell, and that is called the accelerator, and you can change the settings, okay? Because I don't want the students putting their hands in wrong places. We modify and we create a Python code, and the Python code is able to send the settings directly to the relay without you putting your hand over there, okay? If we don't have COVID, probably you can come here and put your settings and so on, but we don't have that. And that is the reason that we modify the code, we create the code in order to send the settings here, okay? Send the settings, Marta, please. Which settings are you sending?
I will send the CT radio.
Okay, CT ratio is 200, isn't it? Yeah.
And in the output window, you can see that it is communicating.
Yes.
And in a while, it will give you an answer that refers of if the relay was writing, if the settings was writing in the relay correctly.
Right now she's sending using Python code over the Ethernet the settings to the relay, okay? And when the settings are done, it will say it's done, isn't it?
Yeah, but it is taking a bit.
Yes, it's taking a bit because there are different communication protocols that we can use for the relay, okay? I didn't tell you, you can use Ethernet, but over Ethernet you can have different communication protocols. And the protocol that it was easier for us to write the Python code is the slowest. But it's working, okay? Come on, it's ready.
It's working.
Working? I don't see from here there. You will do the same in your practice, okay? You will send your settings to the relay, and the relay will be
Now,
ready.
Did you hear the
Yes,
sound?
the tick tick. Do you
Here?
hear the tick
Yes.
tick?
It is the okay saying that the setting was
Successfully.
correctly on the relay.
Okay.
The next step is changing the pickup current at the secondary side.
Okay.
It will be 1.2 amps.
That is the pickup current for the relay.
I will send the signal.
That means if the relay see a pickup current above 1.2 amps, yeah?
I am sorry. I made a mistake here. If you can see the screen, if you put the parameter and you don't press the enter key, you will not write
Okay.
the number or the amount in the code. So you will have this error.
Yes, in red color.
And you see here, you can see that you have an error because you didn't write the setting in the code in order to send to the relay.
Okay, do it correctly. 1.2, enter, and then send the signal, isn't it? Yes, 1.2, enter, change the color.
Wait, send the signal.
Now sending the signal.
It
with the settings.
Okay.
Setting
Now,
done.
yeah, now we will use a defined time delay. In this case, I will use 0.3.
She is using a defined time protection. That means when the current is above that value, it will take 0.3 seconds to open the circuit breaker. That is what she is doing right now, okay?
Now we are ready. The next step is now we already sent the signals to the hill 604.
Okay.
We can do it again just to make sure it's okay.
Yes.
Then you need to select the type of fault that you want to apply to the system. In this case, I will select ABC fault. Next step is apply the fault. This button will apply the fault and will capture the signals, the voltage and current signals of the fault.
Okay.
And then you can see here this is the current signals, the voltage signals, and you see at the moment when the fault starts, the current increase and the voltage decrease. And you can see here the time delay of the since the fault start until the breaker open.
And after the breaker open, the current should go to 0, okay? What you see over here is the steady state. Then we insert the fault, current go through, going high, and the relay sends this increasing current, okay? And you can see how the voltage is going down because we are in fault, okay? And after this period that is related with this time delay, that is around, let's say this is 0.1 and this is around 0.4 something. Well, 0.0334 is the total time for clearing the fault, okay? And you can see after the clear, you can see that in this case the current is going 0. But that is, people will say, no, but that is a simulation because you can do that with Power Factory. To be honest, you didn't do that. What you did was the real stuff. What you did was sending this huge current into the relay, and the relay detect a fault, and it was a 50. That is a fault for overcurrent, and it's tripping, okay? And you can see over here, the relay is tripped, instantaneous overcurrent, and you can see right now that the breaker is open. I mean, this is the real thing. If you are in a substation and this happened, probably you will be scared because you have so many customers without electricity. Because the fault happened, we open the circuit breaker, okay? Right now, we are totally sure that the relay is properly operating and is clearing the fault, okay? Do you have more experiments?
Just
Anything
one
else?
more. The next one is the inverse time.
Okay.
With this experiment, you will see the different curves that the relay has, and you can select different dial of the relay.
Yeah, let me help you. There are two basic types of overcurrent protection, okay? There is the instantaneous, okay? That if the current is above a number, it will trip automatically, okay? You can include some delay, and that is what we call definite time overcurrent, okay? But the curve is like this. From here onwards, the time is constant. But there is another overcurrent functionality, and that is a curve. And that curve, that is time, current time, that curve is basically defined in order that for small currents, the relay take more time to clear the fault, and if the current is extremely high, the relay will take less time to open the circuit breaker, okay? That is the reason that we call that inverse time, because as the current is high, the time is reduced, okay? And that is what she's planning to do now. She's planning to test one inverse time overcurrent protection. Okay, do it.
Okay, first you need to clear the fault.
Okay, you need to do the same in your lab. Okay, when we have this equation, the relay stay open. I mean, still sending the signal, showing the values, and the circuit breaker will be open. Okay, until somebody arrive over there and reset the relay locally. That is one option. Somebody can come here and reset the relay, target reset, or you can do that remotely from the substation using the communication protocol, using the SCADA, using the software from Cell, or in this case, she will use the Python code inside the Typhoon key, okay? Do that, please.
I will clear the fault first.
Yes, you will see something will arrive over there.
And then we reset the relay.
Yes, reset the relay, please. Right now, the relay is enabled.
Course, and you can see the trip signal, the LED of the trip signal is off, and the status of the breaker change again. It is closed, breaker is closed, and the trip circuit is open. Okay, the next step is switch off the instantaneous overcurrent. So I will write down here off. And I will send the signal. And I will enable the inverse time overcurrent. So I will put here the pickup current. I will put 1.2 again. And I will send the signal. What is signal?
Which signal are you sending?
Something is wrong here. Just 1 second.
No problem.
It is saying that it's something wrong here. Okay, I made another mistake here. I'm sorry. I will change it right now.
Another thing is, every time that we have a fault, the device is storing the information, and it's telling you the history, what happened, when happened, and so on. And if the device is having a signal from time, from the clock, and also the device is enabled, is able to capture the signal. I mean, the signal that you saw over there, it can be recorded and stored here, okay? And are you ready, Marta?
No, problem is solved. I just
Okay.
write.
Right now we are receiving signal, current signal, 120 something over there.
Yeah. I am sending the
Settings.
the settings of the inverse time.
Okay.
Overcurrent.
In this case, you can see over here we are using the US very inverse curve. Okay, there are different type of curve. If you allow me, no, it's okay, no worries. Be careful with your head. No, it's not this one. It's this one. Okay. What I want to show you is this is one of the user manuals. Okay. Each relay has, few pages to read. And you must read it. Here, if you took my classes of protections, we use different of those curves, okay? We put the value and calculate the operating time and so on. That was easy, okay? But in reality, inside the relay, you have all those curves, okay? And you can select one of them. In this case, she's selecting very inverse, okay? This is I, this is US, inverse, this is short time, moderately. This is very inverse US, isn't it? Yes, the U3, isn't it? Not.
U3.
Yes, this is the US very inverse curve. In this case, she is using the dial, time dial, number 1, okay? And if you look over here, there are different type dials. And here, I think this is number 1, okay? And this is the multiplier that she is using for the pickup current, okay? What I'm trying to say is if there is a short circuit, that short circuit current will go here, go and intercept, and then you will have the time, okay? Because this is the kind of curve that I'm talking about. This is the inverse time curve, okay? Now, Marta, are you ready for the show?
Yeah, I will send this.
Okay, what I forgot to say, sorry for the interruption, Marta. Here we are using just 3-phase faults, okay? But if you want to test single phase, line to line, or anything else, you are able to do it, okay? Because this is configured and created to test the relay in all the situations. However, you must be aware of the following. In classes, you learn how to set up the relay for 3-phase faults. If you need to do a line to line or line to neutral, there are other settings, okay? And there are different ways to calculate that, okay? In this lab, we are doing just a single phase, or we are including single phase? Yes, we are including single phase, but we are providing to you the settings, okay? In order that you can test the functionality, okay? Okay, ready, Marta? Ouch! We got again a trip, okay? But right now we have a different time, isn't it?
I think, let me see.
Are you sure that you sent the proper?
Let me send again the signals. I think it is not.
Do you need to reset the relay first? Or I can reset from here if you wish. Okay, resetting the relay.
I think I need to make sure this is off.
Okay.
And this is on. So I will send again this signal. Just in order to make sure we are switching on.
Are you okay, Marta?
I'm waiting to the software needs to create the sequence.
Okay, right now you are in a steady state, but the circuit breaker is open, no?
Now it's closed.
I don't see current in the... Let me see here. Oh yes, there are currents here, yeah. Okay, yes.
Okay, I will try again.
Send the fault, yeah. Okay, right now we have a trip.
Yeah, but if you see the
Time is
timing
different.
is different. Yeah.
Yeah, yeah.
Maybe you cannot see so much difference between the time because it is the same fault, but if we select another time dial, we could see another time.
Okay, that could be an option. Let me change the time dial to show them that the thing is properly working, okay? Let's select, for instance, let's go to the top, okay? In order that the fault stay for a bit longer. Let's try 10, for instance. Time dial 10, okay? You reset the relay. Yeah. Okay, sorry that I need to do this, but it's the only way that we can do. I mean, you need to be physically here to show this, okay? It's no other way that. Well, I can find a robot to do this. But. Okay. Okay. Okay, done. What's happened?
No, it's one of from the class that was asking where he was, and I asked him what was this building called, but I should know it. I've been here quite a few times.
But he is not here.
Okay,
No, I think he was at campus and he didn't find us, and he sent me a message now.
Might be
Just-
late little bit.
Yeah,
Now the
I
show
think
is
so.
almost over.
Yes, we are just waiting for this test and we are done, yes.
I will send
The fault.
apply the fault again.
Okay, we are expecting that the time will be,
It's same.
it's the same.
Let me see because there is something in the.
Are you sure that you send the inverse time to the relay?
Yeah, but I think there is missing. Here there is missing setting.
Oh, it's missing one of the settings. Okay, well, we will close the show right now. This is what I have for you for the lab, okay? We will do the following. I will give you later today a document with all the steps, okay? You need to access that computer, that is the workstation. From the workstation, all the software are there, okay? You have the Typhoon Hill. The Typhoon Hill is already connected to here. You don't need to do that, anything else. You just need to open your system and load the model into the computer, and then run the simulation and come here to the SCADA and set the settings and scenes and just collect the data, okay? It's nothing. If you want to try something else, is under your responsibility. If you want to try something different, changing the fault, whatever, but I will be extremely simple in the lab, okay? This is the first time that we are running this. We are doing remotely. We are doing with many, let's say we have been working for 1 year, but to be honest, in the last 3 weeks, we have been developing this for the students, because we have been developing this for us and we understand what is happening, but it's different to make that for the students, that you need to put the hand in the proper place and so on. I mean, if an error happened, we know where to go, but you don't know where to go, okay? Tomorrow we will start the lab sessions. If there is any problem, we will be here, and also we will giving you support. All the labs will be recorded. That means if you have a problem, later we can see what was the problem and see if we can solve the problem and improve from there, okay? I don't know if you have any question at the moment. No questions. Well, this is the lab. To be honest, it's been very hard time, okay? For instance, I didn't like so much protection, because teaching protections on paper is something basic. Anyone can do that. But then I know that those relays are challenging, but I never realized how challenging they are, okay? Basically, because protection engineers, they arrive to the substation and the relay is like this. It's ready for you. I know that the relay, when the relay comes from the factory, the relay is empty, without any configuration. It's like you buying that computer, that there is no software, there is nothing over there, the language, nothing is set. I know that the relays, they come from the utility empty, but I didn't realize how challenging is commissioning. When you are a protection engineers, they are protection engineers doing maintenance, testing. It's coming here, the relay is ready. To be honest, that is a piece of cake. Oh Jesus, I didn't say that, my protection engineers. But all my respect for the commissioning engineers. Why? Because the relay arrive empty, and you need to configure the relay in order to make work the relay. And to be honest, to configure the relay, you need to read more than this, okay? Just the user manual of that is like 3 of these tasks. And try to find where the mistake is. Wow. Okay, well, I just want to tell you that, again, the lab this is the first year that is running. It's possible that there are some issues. Don't be scared, don't complain so much, because we are trying to put the soul and the heart here for you. But if there is problem, we are ready for trying to solve the problem, okay? But if there is a possibility of having some issues, what I want is that my student have the better experience. Probably in 2-3 years time, people can come here, put the settings here. There are many other things that you can do. For instance, you can put an ammeter here and you can measure the current and you can see, okay, this is real current. Right now you see over there, you see over here, and people believe that this is not real, but yes, this guy is producing high voltage, okay? The first task will be over current protection. The second task will be with those 2 guys, and that is distance protection. But distance protection, to be honest, is extremely simple, okay? It's very hard to configure the relays, but from the student point of view, settings is extremely simple, okay? However, I will prepare some documents that they will be extremely simple and extremely helpful for you, okay? Okay, I will say that this is the end of this session. If you don't have any question or any comment. No? Marta, do you have any comment?
No. If you have any question about the use of the SCADA, schematic or Hill SCADA, we will provide a small manual in order to you remember how to use it. The final remark is this software allows you to export the signals in order that you can analyze the signals after.
Those signals, they are extremely helpful, okay? Those signals, they can be exported as figures or as number, and you can take those signals into MATLAB, for instance, and do signal processing, assess data, and so on, okay? And I almost forgot, okay? There is one more practical session that we will be running without marks, without notes, okay? And it's with that device over here. That device is a relay testing. But that device, the Omicron 256, is a relay tester. What I mean is that you can set up this device to test the overcurrent protection, but you will not have the network. What you will do is just, I want to test 125 amps and see if the relay tripped. And you can do that using that very expensive equipment over there, okay? That equipment over there is one of the most expensive here in this lab, okay? Probably a Tesla, yeah, probably. The price of one Tesla, expensive Tesla. Okay, if you don't have any question, I will tell you, thank you very much for coming, thank you for the time. I hope you enjoyed the lab. If you have any problem, any question, please feel free to drop an email. And no worries, I will send the email of Marta. You can complain to Marta. She is the mother of this SCADA. I would like to say thank you also to the people of Typhoon Hill. They have been helping extremely much. Also, the people from Cell, they help a lot in the commissioning stage and settings and so on. And the people from ABB, they have been extremely helpful, okay? It's sad that I didn't have time enough. There are so many equipment here and we don't have so many people with the skills, because that is a very interesting problem. Having people with the skills to work with these kind of things is extremely hard. Many people believe that cyber physical, digital twins, blah, 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 is just something easy. And then when you realize how complex those things are, is when I decide, okay, we need to make this lab open to the public, we need to innovate, we need to include more things inside the lab, okay? Well, if you don't have anything to say, I will thank you very much for coming, and I will see you very soon, okay? Probably I will see you again in YouTube. No, you will not see again my face. This is my office. Don't tell anyone that I am here. Well, to be honest, that is my office. This is my office, my computer, okay? And thank you for coming, okay?
Thank you.
Oh yes, can we have a photo together? Where?
With the equipment,
With the equipment.
if you want, if they want.
Do you want to have a photo together here? But where?
Maybe in this way, in this side.
Yes.
So picture from there.
Yeah.
And we start here.
Yeah, we can put over there. We can be here. Yeah. What I will do is I will remove this.
Yeah. We need a bigger laboratory.
Good morning. Ashish, but you will not appear.
No, it's fine.
No, ladies go on the front. Remember, Marta, what's happened? Come here.
Me too.
You are the mother of this. Put over here. No, it's not. It's okay. I am taller than you. I will be
Okay.
here. You can see. Thank you, Ashish.
Thank you.
He is the official photographer of the lab.
I think one photo without mask, just for.
Without mask. Okay, I will put mine.
Okay.
Thank you.
Thank you. Thank you. You can give tips. No. Just kidding.
Okay.
Okay.
So,
Thank you.
so the FPGA, right? That was a processor unit. FPGA.
No, that is a hardware that is not a processing unit.
Okay.
It's
so
a different. It's a field programming gate array. It's something like that. Yes.
Is that this one? This.
It's inside.
Yeah.
Inside there a CPU and FPGA. Yes.
And that's what is doing the calculations.
Some of the calculations. The calculations are divided between the CPU and the FPGA. Very intensive computational processes, they are going into the FPGA. And the less, let's say, computational hard problems, they are solved inside the CPU.
Okay. But the model type, is that similar to the EMT?
The models that we are solving in the FPGA, they are, in this case with the Typhoon Hill, we are solving AMT models. That means instantaneous values. That is the reason that you can see the sine wave. Yes. Yeah.
So it's similar to the EMT simulations in Power Factory.
Yes, you can get those same results using AMT simulations in Power Factory.
Yeah. Okay.
Yes, but the problem is that with Power Factory, you cannot make this relay trip. There is no way, because Power Factory is a offline simulation software. I mean, it's a perfect software for let's say, for planning, for operation, but for testing real hardware, you cannot do that directly. Okay?
Okay.
Yeah. Okay?
Thank you so much.
No, thank you. See you.
I also have a question about FPGA. It's a very fast system.
FPGA is a kind of hardware that you can configure. It's a very specific hardware that, I mean, what is the problem? They are very different type of hardware. They are assembled hardware like the CPU or the GPU. They have a structure inside that is already predefined for a specific task. The CPU is a general purpose hardware. The GPU is basically for arrays and vectors, and originally was created for graphic
Yes.
purposes. The FPGA is totally configurable. That means that using the proper code, you can create inside any kind of hardware configuration. That is the reason that FPGAs that they are very expensive, because they can change the configuration internally by software. I didn't tell you, but some of those relays inside they have is FPGA. The modern relays inside, instead of having a classical CPU, they are having is a FPGA. Yes, yes. You can read more. I think it's a good idea, yes, that I include some notes about FPGA,
Yeah.
because that is the expensive part, is the computational heavy process inside this.
Yes,
Yeah.
sir.
Yeah. Okay.
Thank you.
And thank you. See you.
See
Thank
you.
you. Bye now. Well, let's close the